Hi, I'm Paul Blanton, President of VEC, and today I'm going to talk to you a little bit about how the DVIA M-Series active isolation system is not sensitive to variations in floor stiffness, much like many of our competitors' products. So one of the things we hear commonly from customers is that they're looking to buy an electron microscope or other type of precision instrument, but they don't have any room on the ground floor. So because of that, they're looking at the second, third, fourth, fifth floors of buildings where the floor stiffness is much less, particularly for steel frame structures. So our competitors have pretty strict floor stiffness specifications, and so installing the microscopes on those floors just simply isn't an option. But with the DVIA M-Series, it is. And so we're going to use this test setup we have here and conduct a series of experiments to demonstrate the performance of the Daeil DVIA M-Series under less than ideal conditions. So, it's kind of talking you through what we have here. We have this steel framed shop fabricated pedestal that we designed, to bear the mass of the Daeil system and these weights, but not to be very stiff. So it's very, there's no intersecting cross members or anything like that. It's really just a steel frame with a half-inch plate on top. Next, we have an older series DVIA M 1000 active isolation system, and then we have these two steel concrete blocks that are going to represent the mass of an instrument. And so the first thing we're going to do is we're going to take these two seismic accelerometers. These are Wilcoxon accelerometers designed specifically to measure low frequency vibration. We're going to show that they agree by taking measurements on the floor. And then we're going to conduct a series of testing showing the transmissibility performance of the Daeil system on this pedestal, and then the Daeil system on this pedestal when we're exciting the pedestal to simulate someone like walking around the microscope on the third floor. To provide data on the stiffness of the floor and compare it to the stiffness of the pedestal, we're going to be using this impulse hammer. It's a calibrated instrument. We basically measure the force applied to the floor, measure the response of accelerometer. We're going to do that both on the floor and on the steel pedestal to compare the stiffness and measure the stiffness of both. So without further ado, let's get started. So the first measurement we're going to conduct is we're going to conduct a baseline measurement with the two seismic accelerometers oriented in the vertical direction. We're going to take this measurement and we're going to compare the data in the frequency domain. And what that's going to allow us to do is validate that that the data agrees between these two sensors, which will validate the transmissibility measurements that we're going to conduct later on. So we have two charts, one on the top for sensor 1 and one on the bottom for sensor 2. These data is displayed in the frequency domain, where the x-axis is the frequency in hertz and the y-axis is the amplitudes in G's RMS, a standard unit. And as you can tell, they agree, which is what you'd expect since they're both in the vertical orientation on the same on the floor next to each other. So now we're going to look at the VC curves, and we see that the VC curves are kind of VCE. Again, the data agrees, which is what we'd expect. And so now we're going to look at the transmissibility. Transmissibility is basically a sensor 2 divided by sensor 1. I see a amplitude of about 1, which is what we'd expect, and the time domain data agrees as well. So now that we've shown that the accelerometers agree, next we're going to test the floor stiffness of this concrete slab. Nothing special about this slab. It's just kind of a thin concrete slab in the back of our warehouse. It's old. It's not like 18-inch poured reinforced concrete or anything crazy like that we sometimes see in TM labs. And we're going to test the stiffness of this not so rigid steel pedestal that we constructed for this testing. So first we'll start with the concrete slab. So what I'm doing is I'm tapping the concrete slab with a known force measured by this calibrated impulse hammer, and then measuring the response with this accelerometer. And as I do this, I have to be careful not to overload the sensor. But what I'm seeing is, pretty good data, kind of 10 to the 8th plus Newton meters, which is, perfectly acceptable for most applications. Okay, now I'm going to save the data and we're going to compare it against this, this pedestal. So one of the things I have to do when I set this up is I have to adjust the input voltage or the sensitivity of this sensor so I don't overload it when I tap it. That's going to be a real risk on this test, is we're going to overload this sensor and we're not going to get good data. So here we go. So as I do this, I'm tapping really lightly because this accelerometer is very sensitive to vibration, and it's hard to tap it lightly enough to excite the pedestal without overloading the sensor. And so this is something, because this pedestal is so, there's not much stiffness to this pedestal, it's much less stiff than what you would see, kind of on the second, third, fourth, fifth floor of a steel frame building. So there we go. So we have, a floor stiffness of the floor of kind of, 10 to the 8th plus Newton meters. And a stiffness of this pedestal, which is kind of just above 10 to the 5th Newton meters. So 3 to 4 orders of magnitude less stiff on this pedestal than on this concrete floor. So now we've shown that the accelerometers agree when measured on the floor, and we've measured both the floor stiffness of this old concrete slab and the lack of stiffness of this steel pedestal that we built for this test. And we're going to show the performance of the DVIA M series isolation system on this pedestal, and show that it performs outstanding even though this pedestal has very low levels of stiffness, much lower than kind of what you'd see in any steel frame structure or any place that could support the mass of a high resolution instrument. So looking at the data, the top chart is the vibration on the pedestal, and the bottom chart is the vibration on the Daeil. As you can tell, there's very little vibration from the Daeil, or from the pedestal transferred to the Daeil. It's actually almost imperceivable. When we look at the VC curves, and kind of see VCD on the pedestal, and not even registering VCG on the Daeil, which is very good. Transmissibility is kind of what's expected and kind of in line with published. And you can really see it on the time domain data, where you have the blue is the vibration on the pedestal, and the red, which is imperceivable and basically stable, is the vibration on the Daeil. All right, so the data looks pretty good despite the fact that this the steel pedestal isn't very stiff. So one of the things we hear is, okay, it doesn't work very well for variations in floor stiffness, but what if someone's walking down the hallway or walking around the microscope room while we're imaging? Can the Daeil handle it? And we're going to show you that it can. So while we take the measurement, I'm going to be exciting the pedestal. You're going to see the impulses in the data, and you're going to see that the Daeil system works great and mitigates it with no problems. Okay, so now we're looking at the vibration on the pedestal and the Daeil. Haven't started tapping yet, so the data is kind of stable in what we saw before. Now that we've started tapping, you really see the pedestal vibration level increase. But as you can tell, the vibration on the Daeil is still very low, barely perceptible on the charts below, which is outstanding. Now we're going to start looking at the VC curves. Again, kind of much the same. VC curves, vibrations, VCC range on the pedestal, barely VCG on the Daeil, which is more than good enough for basically any application that's required. Transmissibility is excellent, and one of the interesting things is as we actually tap more and harder, which you see on the time domain chart on the bottom, the transmissibility performance of the Daeil actually improves, which is amazing. So, very happy with this, and it makes us feel comfortable installing these systems in your labs. Again, you kind of see very high vibration in the narrowband and the VC curves. Well, I hope that was informative, and for us, this was a lot of fun. We've gotten to know these DVIA M-Series active isolation systems really well over the last 5+ years, and we know how well they perform in a wide variety of environments, even in places where the floor stiffness is not where it needs to be for our competitors. Here at VEC, we're very data driven in all we do. All of our recommendations we make are based on data points, and we do the math. And the purpose of setting this experiment up was to show you the data that we know exists and we believe in, so that you feel comfortable putting a Daeil system under your instrument, even if that location happens to be on the 5th floor of a building. So if you have any questions, please feel free to reach out to us, www.vibeng, and we look forward to working with you on your next project.